We've looked at graphing linear equations. We've looked at graphing inequalities. We've looked at graphing quadratic equations using vertex form, using standard form, quadratic inequalities. Now we're going to look at graphing rational functions. And this will not be the last time we graph different types of functions, but we're going to look at rational functions in this video, in this section. So we have a rational function here, rational being in some ratio, like a fraction. And if the numerator, if what's in the top here, has a higher degree than the denominator. So the degree of this polynomial is 2, the degree of the denominator polynomial is 1, so the degree in the numerator is bigger than the degree in the denominator. We can most likely simplify it a little bit. Not always, but most likely we can simplify it. So if we look at that numerator, x squared minus 4, we can factor that. That's a difference of perfect squares. X minus 2, x plus 2. The denominator is still the same. And now we can cancel. Both the numerator and the denominator have a factor of x minus 2. So if we divide those away, we divide those to 1, we end up with just x plus 2 left over. So really we're graphing y equals x plus 2. We've simplified this rational function down, and we're going to use this to graph, which is a lot easier because this is a linear function. It's in slope-intercept form. Y is by itself. So the y-intercept would be 2. There's the y-intercept right there. The slope is the number being multiplied to 1. So the slope is 1. Sorry, the slope is the number being multiplied to x, which is 1. So if you go rise of 1, run of 1, you're going to find another point right about there. And if we connect the dots, we now have a graph for this equation, y equals x plus 2. However, we're not quite done. We've graphed y equals x plus 2, but we got to look back at this original function here, because really this is what we're supposed to be graphing. We've simplified it to make it easier to graph, but we do have to look back here. The problem with this rational function is that you can't divide by 0. When we simplified it, that wasn't an issue. X plus 2 is fine. But back here at the original function, you can't divide by 0. So we have to be careful with these rational functions. X could not be 2. 2 minus 2 would be 0. If x was 2, we'd be dividing by 0. Black holes would happen. Life would disappear. I don't know, bad things would happen. So our domain, the things that we put into this function, has some restriction. So if x is a real number, which we're going with real numbers right now, because that's what we have our graph for, x cannot be 2. So the domain would be x could be any number, but x can't be 2. That's an exception. So we would take that out. Or you could write it like this: x is less than 2 or x is greater than 2, but not equal to 2. So that would be the same concept for the domain. Yeah. So then, so we have our domain. This is what we can put in. So we have a problem with 2. If the domain can't have 2 in it, that means we're going to have some range value that's different too. Because this graph here shows that all real x values work. 2 works in this graph. We get a result of 4. But we shouldn't, because 2 can't go into this function. So our range is going to be a little different too. Our range would say that y could be any real number, but y can't equal 4. And if you look at the graph, you can see that when x is 2, y should be 4. However, x can't be 2, so y can't be 4. This spot right here should not exist. And if you plug that in here, 0 squared minus 4, you would work it out that x just can't be 4. It won't give us the answer that we're looking for. If we back up, there we go. By the way, this is called the roster method. You don't need to worry about writing it in the roster method. The way we would graph this then, because we have an issue where x has to be either less than 2 or greater than 2, y has to be less than 4 or greater than 4, and it can't equal 2, can't equal 4, is we put a little hole there. It's kind of like when you were graphing inequalities. If it didn't quite equal the number, we had an open dot, an open circle, that's coming up again here. And so that open dot, that open circle, we put that hole to represent that we have a space here where there is no value. It works everywhere else, but it can't work here. Let's talk about asymptotes. If you're teaching at middle school, by the way, you have to say this word really, really quickly, sometimes high school too. So asymptotes. We've got this equation. The numerator has a smaller degree than the denominator. The denominator has a degree of 1, the numerator has a degree of 0. In this case, we can't simplify it. It is as simplified as it gets. But we still have to try and work out what the graph would look like. I am going to ask you to graph a problem like this, a rational function. You will be asked to physically graph this because we can simplify it down. I will not ask you to physically graph this rational function here, but you'll be asked to identify some different parts to it. That's what I'm going to get to here. So the y-intercept, we can figure out some parts of this graph. We can find the y-intercept, where the y-intercept is when x is 0. So if we assume x is 0, 0 minus 3 is fine. 0 minus 3 is negative 3. So the y-intercept would be at 0, negative 1. We can plot that point. 0, negative 1 can show up on a graph. That's fine. There it is, right there, 0, negative 1. So we can plot the y-intercept. How about the x-intercept? Let's say x was 0. So that means that 3 divided by something equals 0. I don't know. I'm stuck. I don't think that can happen. Even if you tried to solve this for x, even if you said, well, this is divided by x minus 3, let's multiply both sides by x minus 3, you'd get 0 equals 3, which is a contradiction. This can't happen. There is no value for x that will make this true. And so y cannot be 0, ever. It's just not possible. There is no domain value that will give us a range value of 0. Can't happen. So that's a little bit weird. So we got our y. We tried to find the x-intercept, but we weren't really able to. Let's look at that domain. We talked about the range here where y can't be 0, and we kind of proved that y can't be 0. For the domain, if we look back here at our rational function, you can't divide by 0, 3 divided by something, so x could not be 3. 3 minus 3 would be 0, and 3 divided by 0 would cause chaos. So x can't be 3. How this looks on a graph, these can't equal and can't equal when we have a rational function like this, is we have what's called an asymptote. The x value, where x can't be 3, gives us a vertical asymptote at 3. What this dashed line here says is that the graph, whatever it looks like, will never cross this line because x cannot be 3. So you cannot cross a vertical asymptote. The graph will never, ever, ever cross this vertical asymptote. The horizontal one here, the y equals 0, is a little bit fishy. You can cross a horizontal asymptote. We'll talk about that in a little bit. But this is what the graph ends up looking like. It looks like this. You'll notice that as x gets closer and closer and closer and closer and closer to 3, this y value goes to extreme measures, but it doesn't ever quite touch this line. And then it comes out up here. So as x gets closer and closer and closer and closer in 3, we call that the limit in calculus. It gets super big. The y value gets super big, but it doesn't quite ever touch it. And this y equals 0, y cannot equal 0. You'll notice that as x gets super big and super small, the graph gets closer to that horizontal asymptote, but it doesn't quite ever touch it. And that's what an asymptote is looking at, is as we get to these values, what happens. Let's look at I'll let you pause it and write this down if you need to, but with the horizontal asymptote, there's 2 ways this could happen. Either the numerator has a higher degree than the denominator, I guess 3 ways. And that was like that first example where the numerator has a higher degree than the denominator, and we can simplify it and graph it. The numerator and the denominator have the same value, so x squared or x over x, and that's the second piece here. So if P and Q have an equal degree, then the line A over B is the horizontal asymptote. And I'll show you an example of what that looks like. if P is less than Q, kind of like that last example we were looking at, where the numerator had a smaller degree than the denominator, then the horizontal asymptote is going to be on the x-axis, or x equals 0. So here's two examples. In this first example, the numerator has a smaller degree than the denominator, 1 first degree, second degree. And so this says that if P is less than the degree of Q, which we have here, the x-axis is the horizontal asymptote. So we would say that the horizontal asymptote is at y equals 0. For this one, they have the same degree, x to the 1, x to the 1. So the second piece here says if P and Q have the same, have equal degree, then the line A over B, where A is the leading coefficient in the numerator and B is the leading coefficient in the denominator. So we ignore the 4 and the 6, that doesn't really matter. And the horizontal asymptote is going to be at the line 2/3. So if they're smaller in the numerator than the denominator, if they're different, horizontal asymptote y equals 0. If they're the exact same, whatever these leading coefficients are, it could be 1 and 1, that's going to be your horizontal asymptote. So here's two more examples I'm going to have you try. I'd like you to try and find the intercepts, x and y intercepts, or at least try to. It might be that there is no x and y intercept. But find the x and y intercepts, if there are any. Find the vertical asymptote, find the horizontal asymptote, and stop there. If you want to try and graph it, awesome. But I'm not going to ask you to graph it. I just want you to find this information. So here are the two examples. Pause it. Please try it on your own. I'm assuming you paused it. I'm assuming you tried it on your own. I'm going to put the answers up, and I'll do a follow-up video of finding this information. So for the first one, y-intercept is at 0,2. X-intercept is at -4,0. The vertical asymptote would be at x equals -2. Horizontal asymptote would be at y equals 1. For the second one, the x and y-intercept is at 0, 0. We have two different vertical asymptotes in this case, -4 and 4. And the horizontal asymptote would be at y equals 0, which is right on the x-axis. Like I said, I will do a follow-up video on finding those two answers.